Okay, so let me move over, please, to the next speaker, who is Professor Jack Burns of the University of Colorado at Boulder, and he will tell us about low radio frequency observations from the far side of the moon. Jack, please.
Thank you, Claudio. Let me share my screen here. I want to make sure that everybody can see this. So can you all see the screen now?
Yes.
Very good. Well, thank you. And it's my pleasure today to talk about the astrophysical science that can be done from the far side of the moon using low radio frequencies. And in particular, I'm going to talk about the results of two NASA-funded mission concept studies that we completed in this last year. One for a small satellite in low lunar orbit, and the second is an array on the far side of the moon, which you see a picture of here. Both are intended to take advantage, as we've heard several times, from the truly unique radio quiet environment that's on the far side of the moon. And all of these studies will allow us to really open up for the first time the last window to the electromagnetic spectrum at frequencies below roughly 50 megahertz or so, below the FM band. Here's the problem. The problem from the Earth is that we have a very noisy environment. The top image here is power versus frequency. This is from the LOFAR telescope in the Netherlands, and you can see all of the radio frequency interference, which is coming from a combination of heavily used powerful civil and military transmitters, satellites, and so forth. When you couple that with also effects due to the ionosphere, absorption, refraction, and emission, this makes it very problematic to be able to do observations much below 50 megahertz. Going into space allows you to escape some of the problems from the ionosphere, but as you see with the wind waves data in the lower left hand, this is a plot of frequency versus time. This is a NASA probe that when it was in the vicinity of the moon, but not behind the moon, you can still see that at the distance of the moon, that terrestrial transmitters contaminate with all of these horizontal bands of that spectrum. However, we know that when you do get to the far side, NASA's RAE-2 satellite that orbited the moon in 1972, this plot is, think of this as radio power versus time. The central region here shows the data when the spacecraft was above the far side, relatively quiet, and you can see in this case the foreground, which is the galaxy through which we have to look to do our observations. So as Joe mentioned a little bit ago, we've known since before Apollo that there's a great deal of science potential, and a number of papers were written about using the far side for low frequency observations. But up until recently, scientifically, it's lacked what I would call a killer app. That is a compelling astrophysics problem that uniquely requires the low frequency observations from the moon. That has changed in recent years, and there's two very exciting, what we call in the US decadal level science to be done from the moon. One is the early universe, dark ages, and probing cosmology and deviations from the standard model of cosmology. The other has to do with exoplanets and habitability and measuring magnetic fields and also the space weather around exoplanets. So let me begin talking about the first of the two missions, Dapper. It's this cartoon picture shows a small satellite in orbit of the moon. We take data only when it's above the far side. In the low band, it operates primarily between 17 and 38 megahertz, so below what we can really do from the ground. The problem, the science problem, is illustrated here in this slide. On the left-hand side, you see a cartoon picture of the evolution of the universe, Big Bang at the top, today's universe at the bottom. It's logarithmic in time. Our first picture of the universe comes with the CMB, the cosmic microwave background. And And this is at the period of so-called recombination. That is when the universe is expanded and cooled to the point where the first electrons and protons combine and produce neutral hydrogen. This is the beginning of what astronomers call the dark ages. It's before the first stars form. About a half of a billion years later, those first stars do come into being. They're very massive stars. They emit a lot of ultraviolet light, which then begins to ionize that intergalactic medium that is filled with neutral hydrogen. That period of reionization ends at about a gigayear or so, according to the models. And then we begin to see today's universe, roughly today's universe, with telescopes like the Hubble. Clearly, these time periods in the early universe have been very exciting and important, as indicated by some of the recent Nobel Prizes in cosmology, at least 2 based on space-based and ground-based Nobel Prizes in the last 15 years have been very important, including this most recent one with Dr. Peebles. And then also a few years ago, using Hubble, the realization that the universe is not only expanding, but accelerating in its expansion due to dark energy. The problem we have is we've got this huge gap in information from the dark ages through the end of reionization, which is literally no data. The only way to be able to collect data on this time period is to use that neutral hydrogen and the famous 21 centimeter line, which corresponds to 1.4 gigahertz in the rest frame. When you're looking at the very early universe, though, that expansion of the universe stretches out that wavelength that lowers the frequencies below 100 megahertz. So you have to use the techniques of low frequency radio astronomy to explore it. So what we're proposing to do with DAPR is in fact illustrated here. And particularly, let me draw your attention to the lower left-hand panel. With DAPR, we're going to be doing just a single antenna. And that's usable to explore the early universe because neutral hydrogen is ubiquitous, and the global signal that comes from that can be picked up by a single antenna in a radio quiet environment. So this is a plot. Think of this as the radio brightness versus frequency. And we expect that there are 2 troughs in this spectrum, which indicate where cosmic dawn is and where the dark ages are. Some recent ground-based observations by my colleague Judd Bowman suggests that this trough of the cosmic dawn may be deeper than what we had expected from the standard cosmological model, which is indicated by the dark black dashed line. If so, this requires new physics, and that new physics could be very exciting. It may involve an interaction, unexpected interaction between dark matter and cooling of the hydrogen. There's a second trough, which is only accessible from space in the dark ages. This is at lower frequency. This is an exciting one because it's pure cosmology. There's no astrophysics, there's no stars, no galaxies. And so this is the place to probe for deviations from standard cosmology and new physics. And you see with some of the colored curves in here, these are different models of different cooling rates. So what we're doing with DAPR is to address this question which is posed here: will the observed behavior of the neutral hydrogen redefine our standard cosmological model? So with DAPR, it's indeed a small satellite. It's about 0.8 meters by about 0.5 meters. Most of that volume is taken up with propulsion tanks. We will deploy 2 cross-dipole antennas that are shown here at different lengths. That will allow us to tune our receivers to a low frequency band of 17 to 38 megahertz. The antenna beam is shown on the lower right, kind of a big peanut, if you will, and with very little frequency dependence, so that's very nice. And looking at it, we also extend these observations using secondary resonances to higher frequencies.